Okay, so we are entering our nuclear reactions or nuclear chemistry unit. The first video in this series is going to be nuclear reactions and talking about alpha, beta, gamma decay, as well as positron emissions. So how would I write a nuclear symbol for one of these isotopes? So say that they give me, get my pens here going. Okay, so say that they give me like I don't know, uranium-235, and they tell me to write the nuclear symbol for uranium-235. Okay, the way I'm going to go about that is first I have to write out what my element is. Okay, up here I'm going to write my mass number, and my mass number is 235. That's what they give me here after uranium. And then down here I had to put my number of protons. Well, the number of protons for uranium is always going to be the same, and you can see that by looking at a periodic table. Here, if I go down to uranium, you see that uranium has 92 protons to here. Okay, so I have uranium-235, we said, and it has 92 protons, so this would be my nuclear symbol for uranium-235. Okay. So, radioactive decay. What is radioactive decay? Well, that's the process in which a nucleus spontaneously breaks down by emitting radiation. So, a process in which a nucleus spontaneously breaks down by emitting radiation is radioactive decay. Now, there are different types of particles that can be emitted. So, we can have alpha decay, which has an alpha particle that's emitted. Okay, we can have beta decay, okay, in which I emit a beta particle, or I can have a positron emission, okay, and I emit a positron, or I can have gamma decay, in which I can't really draw very well, but you just emit a gamma particle. Okay, so alpha decay. So an alpha particle is identical to a helium nucleus. And if you look at your periodic table, you can see that a helium nucleus has 2 protons and 2 neutrons. So you have 4 total nucleons. Kind of just talking about the range. Alpha particles aren't very energetic. They have the least energy out of all of the different types of particles that we're going to emit. So they can't penetrate nearly as much. So pretty much they're just going to be able to go through a little bit of air. Most of the particles are going to be stopped by just a few centimeters of air, a sheet of paper, or even the dead layer of the skin on our bodies. So externally, these don't cause very much in the realm of health problems. But if you ever see any problem and it has a helium nucleus, think alpha particle, alpha decay. Okay, here's the general formula for alpha decay. You have an unstable atom. Alright, so here's my unstable atom with my atomic mass, or my mass number up here, my number of protons here. Okay, and we said that with alpha decay that we lose 2 protons and 2 neutrons. So if I lose 2 protons and I lose 2 neutrons that both come from my mass number, I'm going to subtract 4 from my mass number. And I lose 2 protons, I'm going to subtract 2 from my number of protons. And notice here how that gives me a completely new element. Alright, when I change my number of protons, I get a new element. So I'm going to have a more stable atom here. And with a 4 subtracted from my superscript, a 2 subtracted from my subscript, and then I have to write out that the alpha particle was emitted. Now, looking at this formula, you know that it's balanced when I have the same number of protons and neutrons on each side. Alright? So I have the same number of protons and neutrons on both sides, same number of particles on both sides. Okay, so let me move on. So I'm going to rate on 226 to 222, 88 to 86, so I subtracted 2 there, subtracted 4 there, and if I just and then you notice that my helium right here is my alpha particle that gets emitted. Okay, so here's just kind of an example, kind of visualizing it. This right here loses 2 neutrons, 2 protons. as the alpha particle here, and I'm just left with radon. And so this is a much more stable atom. Okay, so here's just a simple little example here. We know that we have to subtract, so now we have our radon, so if we do another alpha decay, then we have to subtract 4 from this top number, so I'm going to have 218, okay? From this bottom number here, I got to subtract 2, so I'm going to have 84. To know what element it is, that's when I'm going to go to my periodic table and find out which element has 84 protons, which happens to be polonium. Okay, so my answer would be polonium 218, and that would be my answer of what it decays to. Okay, so here's just another example, kind of working backwards. So if I know that I have 230 here, I know that I had to have subtracted 4, so I'd have 234. I know I had to have subtracted 2, and if you remember that 92 is for uranium. So I can go back to my periodic table and look at that, but uranium is what has 92 protons, so that would be my particle. That would be the atom that was formed there, my isotope. Okay, so now beta decay. So beta particles are fast moving, is when a fast moving electron is emitted from the nucleus of an atom. So basically an electron is going to be emitted because a neutron no longer wants to be a neutron. It can be more stable as a proton, so it's going to lose its negative charge to become that proton. Okay, so a neutron changes into a proton and an electron, and the electron just leaves the nucleus. Okay, so that electron is just going to leave. Okay, so as a result of beta decay, the nucleus has one less neutron, but 1 extra proton. So what that means is that my mass number is going to stay the same. So for beta decay, mass number stays the same. What ends up changing is my number of protons. So if a neutron becomes a proton, I have 1 extra proton. Okay, so 1 fewer neutron, 1 extra proton. So my atomic number, or my number of protons, increases by 1, and my mass number stays the same. Just a couple extra notes on that. Beta particles also aren't very high energy, but they can penetrate farther than an alpha particle. They can travel about 10 feet in the air. In human tissue, they're really only going to be able to travel a few millimeters, so just a few millimeters into your skin and tissues. Shielding wise, they can be shielded with thin layers of plastic, glass, aluminum, wood. They say not to use lead, but I mean because you can increase the production of X-rays. And so these are a little bit more of a biological hazard than the alpha particles tended to be. Okay, here's my general formula for beta decay. Okay, and you're actually going to see this in you could possibly see this in different ways here. No. Okay, so here it shows it as a beta, and you could see it like that, but another way that you'll see this written is that this is also a beta particle right here. This electron with this -1 here. So you're going to take your atomic number, or your atomic mass here, your mass number is going to stay the same. Your number of protons is going to increase by 1, and that's just the general rule that you're going to see there. Okay, so an example. So remember we said that our top number is going to stay the same. So my mass number stays the same. My number of protons, well, one of my neutrons becomes a proton. So I add 1, so I have to add 1. That doesn't change at all. Okay, I always have to make sure I put my particle there. And then this is going to be whatever has 91 protons on our periodic table. Okay, so if we look back at our periodic table, find out what has 91. 91's protactinium, alright, and that's going to be Pa, which is, I can say, a lot easier than that word, right? Alright, so this would be what I get as my answer right there. Okay, so that's what is the product, the more stable nucleus of my beta decay, my more stable atom. Okay, here's another example. It's just kind of working backwards. Okay, so remember this number stays the same. This number I had to add 1, so what plus 1 equals 81? 82. Okay, what has 81 protons? That would be thallium, or Tl. Okay, so that right there is going to be my answer. And just kind of a point to make, 210 is equal to 210 plus 0, so that part's balanced. 81 is equal to 82 plus negative 1. So you actually do have a balanced, a balanced nuclear reaction here, because my number of nucleons is the same on both sides. Okay. So gamma decay, gamma rays are not charged particles like alpha, it's a symbol for alpha, and beta particles. Gamma rays are electromagnetic radiation with high frequencies. So remember we talked about this in previous units, and we talked about gamma rays. And gamma rays are going to be your highest energy form of electromagnetic radiation. They're going to have a high frequency and a long wavelength. So kind of a review on that. So when atoms decay by emitting those alpha or beta particles, sometimes the nucleus, the nuclei of the new atoms formed, they still might have too much energy to feel completely stable. So what they're going to do is they're just going to release gamma rays to kind of get rid of that excess energy. They don't want that excess energy anymore, so they're going to get rid of it in the form of a gamma ray. And they're going to be high energy photons. So here's just kind of a couple of examples. This 90, my bad, that should be over there. I'll kind of throw it over there. Okay. Right. Okay. So as you can see, we go through alpha decay because we see that we emitted an alpha particle, and you'll also see that we have a gamma ray are also emitted. So that doesn't really, you don't see any change in your nucleons because it doesn't really have anything to do with those particles. It just has to do with extra energy being released. And obviously these numbers go up here. I don't know why I copied like that, my bad. But this is a beta particle, so first you had a beta decay and an excess gamma rays were also emitted. Okay, nuclear reactions can also occur when the nuclei of atoms react with bombarded particles like neutrons, charged particles, etc. So if I have a nucleus and it reacts with a neutron, okay, then you're going to see this top number increase by 1 and this bottom number stay the same. Because my number of protons isn't changing, I'm just adding a neutron to my nucleus. Okay, and sometimes that's going to cause gamma radiation to leave because it's not very stable, it's very high energy in this form. So if I add a neutron, my top number is going to be what changes. Oh no. Okay, let me get back to that last slide here. Positron decay. Okay, so for positron decay, it's kind of going to be the opposite of beta decay. Instead of a neutron wanting to become a proton is going to become a neutron. Okay, so the proton is going to lose its positive charge. So it's going to lose that positive charge, and we're going to call that a positron. Okay, so we're going to call that a positron. So my atomic number here, or not my atomic number, sorry, scratch that. My mass number here is going to stay the same. Okay, it stays the same because we have one fewer proton but one extra neutron, so that's going to stay the same. And this number right here, my atomic number, or my number of protons, is going to decrease by 1. Okay, so it's getting rid of one of your positive charges, getting rid of one of your protons, and changing it into a neutron. So this number is going to go down. So in beta decay, you saw it go up. In positron emission, which I should say positron emission, it's going to go down. And notice this is still balanced. 22 is equal to 0 plus 22. 11 is equal to 1 plus 10. Okay, so proton changes to a neutron, and that's what you see with that. So that's the end of that video right there. Hopefully you gained something from that. I'm going to make one more video. I'm going to go over half-life with you. But the majority of the test is going to be on these 4 different types of nuclear equations and radioactive decay.